Good morning, students. In the last class, we have seen how light gets refracted when it passes through a prism. And we also saw the concept of angle of minimum deviation. And then we derived an expression connecting the angle of deviation delta and also the angle of incidence and angle of the prism. We derived the expression delta is equal to I1 plus I2 minus A, where I1 is the angle of incidence, I2 is the angle of emergence, and A is the angle of a prism. And now we are going to derive another equation connecting the refractive index of the prism and also the angle of minimum deviation. Yesterday we did this derivation with the help of a diagram showing a prism, and this is an incident ray, this is the normal, and angle of incidence is I1, and after refraction it travels bending towards the normal, making an angle of refraction R1, and at this point let the normal be N2, and at this point again it gets refracted as it enters the rarer medium, that is air. Let this angle be R2 and the angle of emergence is I2. Now if the incident ray go on straight, or this is the direction of the incident ray and this is the direction of the emergent ray, the angle between the incident ray and the emergent ray is called what? The angle between the incident ray and the emergent ray. What do you call that? Delta. It's angle of deviation. So yesterday we have derived this expression, and today we are going to derive a relation between the refractive index of the medium mu and also the angle of minimum deviation delta m. So let us see how we can do. You have to use this equation that delta is equal to I1 plus I2 minus A, and also you will have to use the equation R1 plus R2 is equal to A. We saw these two equations yesterday. So we will use these two equations in the derivation. Also, we know that at minimum deviation, when delta is equal to delta m, angle of incidence I1 will be equal to the angle of emergence I2, and the refracting angles at both ends will be the same, that is R1 is equal to R2. So within this condition and using these two equations and also using Snell's law, we will end up with the relation between the refractive index of the prism and also the angle of minimum deviation. Can you tell me what is Snell's law? The generalized Snell's law? What is Snell's law?
Sin theta 1 equal to mu to sin theta 2.
Mu 1 sin theta 1 is equal to mu 2 sin theta 2. So here mu1 is the refractive index of the first medium. The first medium is air. So mu1 will be equal to 1. And the second medium is a prism. So it is made of a glass having refractive index mu. And the third medium, this is again air. Therefore, the refractive index will be 1 again. So here mu1, I am considering this refraction at this point. So mu1, this one, so we have it 1, and sine theta 1 is I1. Sine I1 is equal to, when it enters the prism, mu2 is mu. So mu sine What is the angle of refraction? R1. So R1. So I can write here mu is equal to, when I take sine R1 to the side, it will become sine I1 by sine R1. Right? Now, let us take this equation. Delta is equal to mu I1 plus I2 minus A. So, we have delta is equal to I1 plus I2 minus A. Now, when delta is equal to delta M, we can write I1 is equal to I2. So, I1 plus I2 can be written as 2I1. Can I write like that? Because I1 and I2 are the same. So, I1 plus I2 can be written as 2I1. So, let me write delta M instead of delta, and I1 plus I2 is equal to 2I1 minus A, or 2I1 is equal to, A can be taken to this side. So, A plus delta M. And if I take I1 is equal to A plus delta M divided by 2. So I got an expression for I1. Later, I will put that in this equation. Let me number this as equation 1, and I will put I1 in equation 1 later. Now, I also want to find an expression for R1 and put that in this equation. For that, let me use this. R1 plus R2 is equal to A. But we know that if delta is equal to delta M, R1 is equal to R2. Therefore, when I write R1 plus R2 equal to A, instead of R1 plus R2, I can write it as 2R1. So, 2R1 is equal to A, or R1 is equal to A by 2. So I got an expression for I1 and also R1, and I will put both in equation 1. So putting I1 and R1 in equation 1, I will get mu is equal to sine A plus delta M by 2 divided by sine A by 2. So this is an equation which you have to memorize. What is the relation between refractive index and the angle of minimum deviation? Mu is equal to sine A plus delta M by 2 by sine A by 2. Can you memorize this equation? Is the derivation clear to you?
Yes.
Okay, so the equation is mu is equal to sine A plus delta M by 2 divided by sine A by 2. So we learned 3 equations from this topic. One is delta is equal to I1 plus I2 minus A. This equation should be memorized. Then R1 plus R2 equal to A. And the third equation is mu is equal to sine A plus delta M by 2 whole divided by sine A by 2. Now, there is one more equation which we need to derive and memorize. That is related to thin prism. Thin prisms are prisms for which the angle of the prism will be 4 degree or 6 degree. Usually it will be less than 6 degree. Okay, so what is the angle for a prism whose principal section is an equilateral triangle?
60.
It will be 60 degree, right? So if it is a very thin prism, angle of the prism will be less than 6 degree. So what is a thin prism? They may ask you in multiple choice question. a thin prism can have the angle, and they will give different options. Remember that a thin prism will have an angle less than 6 degree. Usually it will be 4 degree or 6 degree, 6 or less. So let us take the case of a thin prism. For a thin prism, I1 and I2 will be very small, and R1 and R2 will be very small. So when theta is very small, what will be sine theta? As theta is very small, what will be sine theta?
Less.
Sine theta will be
0.
theta itself. What is sine 0?
And
0. So when theta is very near to 0, which means it is very less, sine theta can be approximated to theta. I think you must have learned this in trigonometry. As theta tends to 0, sine theta tends to theta. So if theta is very small, we can consider sine theta as theta itself. We will use this idea, and also we will use the idea that for a thin prism, I1 and I2 are very small, which means they tend to 0. And again, R1 and R2 also tend to 0. That means they are very small. And the angle of the prism will be 4 degree or 6 degree. This is the peculiarity of a thin prism. Now let us see what is the deviation for a thin prism. For a thin prism, let us consider Snell's law. We saw that for Snell's law, we can write mu is equal to sine I by sine R. Sine I1 by sine R1, right? So, since as the I1 goes to 0, sine I1 will be equal to I1 divided by R1. So, I can write I1 as equal to mu into R1. Is that clear?
yes.
Okay. And in the same way, if I consider refraction at the other end, when light passes, if I consider refraction at this end, here the angle of incidence is, emergence is I2, and the refracting angle is R2. So when I apply Snell's law here, again I will get mu is equal to sine I2 by sine R2. I'll tell you how. Here the refraction mu, and here you have 1. So 1 into sine I2 will be equal to mu into sine R2. So mu will be equal to I2 divided by R2. Is that clear how I wrote this equation? Say yes or no.
Yes, teacher, got it.
Okay. So again, we know that I2 and R2 tends to 0. So I can write this as equal to I2 divided by R2. So I can write I2 is equal to mu times R2. So I got an expression for I1 and I2. Now I will substitute that in this equation. So I get delta is equal to, instead of I1, I can write mu R1. I'll rub this because I don't have space. Mu R1. Instead of I1, I have written mu R1 minus, instead of, plus, instead of I2, I will write mu R2 minus A. Mu is common here, so I can write this as equal to mu times R1 plus R2 minus A. But R1 plus R2 is A, so this is equal to mu A minus A, where A is common, so I can write delta is equal to delta is equal to I can take A outside. A into mu minus 1. So this is an expression for thin prism. Whenever the prism is thin, you can see here, is there angle of incidence in this equation? Is there angle of incidence?
No.
No.
So for a thin prism, the angle of deviation does not depend on the angle of incidence. It will be a constant. Whatever be the angle of incidence, the angle of deviation will remain a constant. It depends only on the refractive index of the prism and also the angle of the prism, which will be very small. Angle of the prism will be very small. So this is an expression for thin prism. Did you understand how we derive this expression?
Yes.
Yes, teacher. Understood.
So we have learned 4 equations in this topic which you have to memorize. One is that delta is equal to I1 plus I2 minus A. Second one is R1 plus R2 equal to A. Third one is mu. The refractive index is equal to sine A plus delta M by 2 divided by sine A by 2. Okay, so these 4 equations, this is for thin prism, delta is equal to A into mu minus 1. These 4 equations must be memorized to solve problems. So that's all I wanted to discuss today. Now I will hand over the platform to Hasina to discuss dispersion of the prism. So Hasina, are you ready?
Yes.
I will
But
share
if I don't
your
talk for a second, it means that my network has some issues. It's reconnecting.
Oh, okay. Can I share your screen now?
Yes, yes.
So I'm sharing. Can you see this? Okay, let me. Can you see the screen now?
Yes. Teacher, you're gonna record the presentation also?
Yeah, why not? It's okay.
Okay.
Yes,
Should I start?
Okay.
Where is Hasina?
Yes, I am here. Okay. Good morning, everyone. My topic for today is dispersion of light through a prism. So before starting this topic, I would say a few things about light. Well, we know that a white light is not actually a white light. So uh, there are millions of colors in a white light, but for simplification, we just say that there are 7 colors: violet, indigo, blue, green, yellow, orange, and red, the rainbow colors. But mainly there are millions of colors in a white light. So there is a question that why does the light have different colors and what is the difference between each light? Red light, blue light, green light, and the other lights.
Yes, Hasina.
She left, teacher. She will join again.
Clever.
I'm sorry, reconnecting again.
Okay.
Okay, so if we compare the light with sound, we know that light and sound both are energies, right? They are waves. So take a piano for instance. We know that each of the when we press different keys, they make different sounds. The difference between these sounds are they have different frequencies. That is why they have different noises in them, different sounds in them. Similarly, different colors of light are having light waves. These light waves are having different frequencies. So the frequency of red will be different from the frequency of from the green light. So the color of blue light will be different from the yellow light. That is why this whole different frequencies of light make up the whole white light. Now we will see this presentation. Here we can see that when you shine a light on a prism, it splits the white light into its constituent colors. And the splitting of white light into its constituent colors is known as the dispersion of light. Is anyone listening?
Yes, yes.
Yeah, carry on.
So, and this splitting of white light in its constituent colors is known as the dispersion of light. And the band of colors that we can see that is obtained by the dispersion of light, the band of colors which are the violet, indigo, blue, yellow, red, and orange. These colors, this band of light is known as the spectrum. Okay. So, as we have discussed that the spectrum band contains millions of colors, but here just for simplicity, we can only see. Okay. So the examples of where we have seen a spectrum, the best example for this is a rainbow on the back of a CD. The rainbow where the sunlight splits into its different colors. When the sunlight splits into different colors, and we can see a rainbow after rain. Of course. Okay, and
Should I change the slide?
yes. Okay, in this figure, this figure is pretty much simple with the experiment that Isaac Newton did. He did the experiment he discovered the dispersion of light by this experiment. Okay, so this figure is basically the same thing. He made a small hole at the window of his room, and when the sunlight falls on the wall of the room through the hole, and he placed the prism right on that place where the sunlight was falling on the wall through that hole, and he saw 7 colors instead of a white light. So Newton has named this band of 7 colors as spectrum. He saw these all colors that I've just mentioned: violet, indigo, blue, green, yellow, orange, and red. So from the spectrum, we can see that the deviation of red color is minimum and the violet color is maximum. I'll get into that later, but just for now, you just have to know that the deviation of red is maximum and the deviation of violet is minimum. Here we can see that in the spectrum.
Okay. Should I?
The deviation. Yeah, I'll tell you. The deviation of yellow color is in between red and violet. So the deviation of yellow color is also, we call that mean deviation, and the yellow ray is called mid ray. Next slide. Okay. Now I will talk about the causes of formation of the spectrum. How a simple glass prism is able to split the white lights into different colors. For this, we need to know the concept of refraction. We know refraction means bending of light. So we take a polychromatic light, which is the white light. Polychromatic means in a white light we can see different colors, right? That is why a white light is known as a polychromatic light, and monochromatic means single light, only one light. So in yes, so in this prism, yeah, one important point to remember is that different colors of light have the same speed in air. That is 3 into 10 to the power 8 meter per second. So all the 7 colors travels at the same speed in air, but the moment they hit the glass of prism, the speed of the different color changes in the glass prism. The red has the maximum speed and the violet has the minimum speed. So because of I'm very sorry again. Okay, so because of this change in speed, of different colors, they bend at different angles in the glass prism. So we can say that this is how they split there. And then there is another refraction when these different colors are coming out from glass to air. This is how the glass prism is able to split the white light into its constituent colors. So the important point for us to remember is that all the colors have the same speed in air, or else otherwise we will see rainbows everywhere right now. That is why they have the same speed in air, but in any medium, glass or any other medium, different colors have different speed. That is how they split up.
Okay.
Yes, and also this amount of bending of the color of light, it depends on the refractive index of the medium of the prism. Light of each color has a fixed wavelength. As I've said before, when I compared light with sound, they have their own different frequencies, right? So that is how light of each color has different fixed wavelength. So the relation between the refractive index and the material of the wavelength of the light, we can express the relation between them by an equation which is put forward by the scientist Cauchy, and his equation is known as Cauchy's equation. His equation is the refractive index of a medium is equal to a constant plus another constant divided by the wavelength of the light plus another constant divided by the wavelength of another light. Okay, and it goes on and it goes on. Here mu is the refractive index of the medium, and lambda is the wavelength of the light, and a b c are the Cauchy's constant. Okay, so from this equation it gives us an illusion that when the lambda or the wavelength, when the lambda increases, the refraction of the refractive index decreases. So if the red light if the red light, its wavelength is more than the violet light, we know that if the wavelength of the red light is more than the violet light, then the refractive index of the red light will be less. Uh, this is shown in the graph.
Yeah, it's shown in the graph, right?
So the refraction, yes.
Okay, continue.
So the refractive index decreases with the increase of the wavelength, and it also increases with the decrease of the wavelength. When the wavelength increases, the refractive index decreases, and when the wavelength decreases, the refractive index increases. Okay.
Okay. Thank you, Hasina.
That's
I think you did it really well. Is it clear to everyone?
Yes, teacher, clear.
Are there any doubts?
No.
No, I guess.
No, it was really clear. Thank you very much, Hasina. You did it very well. Now the next person is the next person to